Is the presentation visible?
Yes,
Yes.
presentation is visible. You can just put it in the full screen mode.
Yes, sir. So, sorry. So good evening, panelists. So today we have come across a very important design, which may turn out to be a revolutionary design for the future. Hence, now we start about our design and assembly. First of all, the idea of our space station Avighna is the main aim is to inculcate space tourism in the future. So in order to bring about space tourism in the future generation as a main purpose, we have devised a concept in which we will be able to simulate a gravitational field, which is much similar to that of the Earth, or the acceleration due to gravity around 9.8 meters per second square on Earth. We will be able to simulate that using the distances um, between these modules and the angular spin which we have planned to um, inculcate in this. And also one of the most important aspect of a design is that it is an expandable design. In the future, we will be able to add many number of tourist modules, etc. Over here, as marked, you are able to see different modules, which we will be discussing in the future. The important modules over here. And initially, our design basically consists of 8 modules, which are placed neck to neck. And there are two collection of modules, or we call as a bus, which is called the Octagon, whose plane is perpendicular to the direction of motion of the space. Now, why did we choose the shape Octagon? So the shape Octagon is basically for our tourism purpose, which is basically to inculcate the gravitational field effects on each of these modules, because those modules will be the tourist modules where all the tourists will be able to reside and do other recreational activities. And through +1, +2 levels, we know that gravitational equal amounts of gravitational force acts at equal distances. So using this concept, if we set this structure at a particular angular speed or an angular spin, we will be able to get about a value approximately equal to 9.8 meters square for the acceleration due to gravity. And we had also calculated, as per taking the radius of over here, the radius of these beams, or we call the transfer modules as 50 meters. So taking radius is 50 meters and the acceleration due to gravity is 9.8, we approximately get an angular velocity of 0.442 radians per second. And as per calculations, uh, across the diameter of our modules, we get a difference of from 9.8 meter per second square to 10.38 meter per second square across the diameter. And across the linear direction of modules, we get a difference of 9.8 to 9.823 meter per second square, which is not much, which is great for sustainability. Now, there are several modules, but there are few fundamental modules that we did focus on, and it is one of the most important, or um, most important aspect of our design is this. So initially we start with the power module. It is very easy to say that power module will be the easiest, it will be the most important aspect of any space station. So hence a power module consists of the structure with two solar panels which are arranged usually perpendicular to each other, and hence the um, most important source which we'll be using for all the requirements on boards are the electricity received we will be generating from the solar arrays. And hence also this is the first module to be sent to space, so that we can do other operations on board after the docking. The second module is the ECLSS module. It is an environmental control and life support modules. As the name suggests, it is for the it is a module which will make possible life on board and also control the atmosphere on board. Which means basically controlling the atmospheric pressure, fire detection, waste management, etc., which all we can do in Earth. So this basically supports the system. And the main motive of this module is basically to make sure that the ECLS system is working up to the par before the habitation begins. So this is the secondary module which will be reaching the space, and this is just a testing module which will later on be integrated with the entire space station for making life possible in the future. The most important module of our design is called the Octagon. Through this CATIA, or the 3D modeling model which I made, over here we can see in the center is a bearing assembly, and this is basically our connection to the main dome. The most important aspect of why we chose a bearing assembly is because we want the octagon to have a spin with respect to your main space station. We want the main space station to be stationary. That's why we'll be using a bearing assembly. And the bearings we chose for this is the roller bearings, because roller bearings are excellent in handling radial loads, which we intend for. And these individual modules, basically the 8 modules over here which you see, those are basically your space hotels or the laboratories, which we'll be discussing later on. And these beams are basically your support beams. These support beams have a diameter approximately approximately 2 meters, which will facilitate the movement of people and also the goods between the habitation modules and the main space station. And the individual triangular pods which you can see in the front view of this thing are the transfer pods, which basically acts as airlock. Those are mini airlocks which separate the environment between each of these modules and also improve the structural integrity of the structure, because over here we'll be avoiding sharp edges. That's why curved edges are much better. And from here we can basically tell the modules which we have. We have divided the 12 modules from the 16 modules and designated those as the space hotels. Now the 2 out of the 4 modules left can be designed as the the modules for research and cultivation of food, because in future if there are tourists coming, food cultivation becomes an important aspect. And also this is one of the point we'll be discussing in the future. And uh, and the remaining modules are basically for the recreational facilities, which are for the games, exercise, and other leisure activities. So exercise is one of the most important things to be done on the space station, in order to because every human being will be facing microgravity effects on their bones, bodies. So in order to limit those effects, exercise is important, and hence this is important. Hence, one of the most important design of the octagon is the rim or the side panels. So the rim or the side panels which we designed, those are basically designed to embed solar panels. So these solar panels, along with the solar panels at the power modules, will basically ensure a 360 degrees view of the panels facing the sun, which will ensure your maximum energy conversion, and hence there won't be a limit or a problem in the electricity on board. Uh, this is also an important module which every space station does have. It's a docking module. Our design initially consists of 6 radial and 6 perpendicular modules, and a center circle over here, which you can see, or a cylindrical opening in between. Those are basically for the launching of janitor satellites and also stationaring or docking different space debris, which we'll be collecting for maintenance and or for refueling and other operations, which we'll be discussing towards the uh, near end about the space debris collection. And hence, this serves as a two-way factor of debris management and also docking of many space stations or satellites. And over here also, these docking stations as we told, it's an expandable feature, our space station, and hence these docking modules could be added easily and as per requirement of the future generations. And one of the most important um, module related to the tourism factor is the observatory module. So this observatory module is basically consists of a big glass dome. This big glass dome provides a panoramic view of the cosmos and the Earth to the tourists. Hence, we can also say that yes, glass is there, but glass does poses a threat to the space station as well as the tourists. So how can we change it? Though we'll be using a top-notch glass facility, we also have a facility known as a nose cone. This nose cone is basically built of a material known as Whipple shield. To be specific, we will be using we will be using multiple shock shields over here. So Whipple shield basically is a hyper velocity impact shield. It does prevent the micro debris from causing problem towards the inside of the module. And also the glass which we'll be using here, we have thought of using the glass ceramics as they are cost effective and ease of availability, and they are the best in thermal insulation, and they are strongest till date. Not to be strongest, but strong with respect to effective cost effectiveness and ease of availability. Now, what is a Whipple shield? As the diagram we can see, it is a multi-layer insulation. It is a hypervelocity impact shield. So we know the micro debris do travel between speeds of kilometers per second, to be specific, between 3 to 18. So this basically made up of outer bumpers and inner. There are many layers inside depending on how strong you want it to be. So the outer layers are basically made of aluminum, and the inner layers are basically made up of 6 layers of Nextel and 6 layers of Kevlar, which are both excellent thermal resistance and impact fibers. And these bumpers are basically used to break up the particles and disperse it, and disperses energy, to be specific, not the different particles. So these energies will be dispersed throughout the entire surface of the nose cone, and hence it will be uh, uh, able to dissolve the micrometeorites easily. And this will be proceeded by one of my colleagues.
You're
Evening,
not audible
Lilith.
actually.
So the next,
Oh, we can hear you.
Sorry,
am I not audible?
yes, your
So, so the next section is about the robotic arms. The purpose is for docking and collection of debris. On basic level, we have used two types of robotic arms: a shutter structure and octopus armature structure. This role in assembly of modules and has 7 to 8 degrees of freedom for easy and smooth movement. They are interconnected rails like structures engraved on each module, and adjoining edge. Now, the advantage of this shutter mechanism for debris collection is that this debris from all sides equally and uniformly, unlike the robotic arm gripping, which can lead to unwanted force zero. Uh, so the next points are about the relative structure, relative motion, the structure of the
Yes,
robotic
you are not
arm.
audible.
Next slide.
You are not audible.
Hello, am I audible now, sir?
Yes, you are, but you will have to repeat the last point because we have not heard it.
Okay, so the last point was about the structure of the shutter mechanism, which was the relative motion between the spur and the crest and arcs, which join the uh, different structures inside the armature of the robotic arm. Next slide.
Basically, what we understand is basically this is the mechanism which we're using for debris, collection of the debris, right? Or
For
for holding something.
yes, for debris collection and for welding and debris collection. For docking, the a different robotic arm has been used, which is in the next
Okay.
slide.
Yeah, go ahead. Go ahead.
Okay, so next slide. Rahel, next slide.
I've already.
Yeah, so this armature, okay, so this robotic arms define the docking and process outside the scene. Outside, then different modules are arriving station to uh, the modules that and on the space station. Slide, and
I think your voice is breaking. If there's issue with your connection, then one of your colleagues can explain the slide.
actually, sir, this is my part. That's why. Is it clear now, sir?
It's fine now.
Hello.
Yeah, just try
Okay.
again, please.
Okay. So the next slide is about the assembly of the space station. That is how the space station stands in the orbit. So the very first step is to send the system. Power system was explained by Rahul. A single power system a module will be sent to the orbit, and then the ECLS part, which is the life support system, for supporting life on the space station for further research and development. Now, adjacent laboratories will be sent for developing like developing some research so laboratory sent. Now, for the Octagon assembly, assembly will be waiting for in the Octagon. Next is being in the of for one launch now, but in future it can vary according to the launches. Next is habitation modules for more like things coming onto the space station, like space tourist and more research and development guys. Next module for further modules to be docked, like sweeping modules and uh, thermogens, etc. And finally, we will activate the debris decelerator when the space station is collectively ready for the whole mission. Uh, okay, so the next subsystem is about the thermal environment of the space station will be located at. So the environment, next slide, right? Environment of base station will be rated ranges from ranges in temperature of 250 degrees Fahrenheit to -2 accompanied by
Sorry,
heat
IIT,
waves
but we
from
are
the
not able to
solar
understand anything because
from
it
the
is
sun to
in
the
between
middle
Yeah,
voices that we are receiving.
of the earth.
Ashish,
Next
actually,
slide.
your slide is also not moving.
So, uh, see you crack, see your voice cracked a little bit. Can you speak again?
Could you
Hello.
please hold on? Could you please hold on for a moment?
Yes.
Uh, okay, so I'm continuing. The next part is about the insulation of the space station, which includes the MLI, the multi-layer insulation, which is used to protect the ISS, and so are we using as there are no further research and
Team
developments
Avighna,
in
your
this
slides are not changing
MLI.
actually.
Your slides
Next
here,
is
the slide here is
reflective
not
cellular
changing.
mesh of aluminum.
Sorry, sir. Actually, we have changed the slides from our side.
Could you please,
Do you want us to reshare?
could you please remove your slide once and put it again?
Sir, I'm on the insulation part.
Maybe some connection issue.
Yes, sir. Fine. I'll just do it in a minute.
Rahul, can you just go back and
Yes, sir.
proceed it
Yes, sir.
again?
I'll reshare the slides.
Yeah.
This is it visible now? We are in the insulation slide right now.
No, not yet. We are waiting for that.
It's actually shared from our end, sir.
Yeah.
Ah, it's coming. It's coming.
Yeah, now you can start.
Yes,
Maybe.
yes.
You can start from here.
Okay, sir.
And start from your left. Ah.
Okay, sir.
Yes, Rahul. It's clear. You can go ahead.
Should I continue? Okay, so the speaking about the insulation which was and the ISS, which so are we using in our space station as there are no further research. A multi-layer insulation would be used, and in addition to that, reflective slash of lead, aluminum layer and captain would be used, which are tested to uh, tested to the space environment. Uh, now, next slide.
Continue.
Rahil, next slide.
It's actually changed from my end.
Okay. Now, see the slide.
Yeah, you are not audible here right now. Can you
Okay.
hear us?
So the next slide is about the
Yes, yes.
ejection of
Please go ahead.
heat. Yes. Sir, if the slide is changed, the next part is about the ejection of heat, which is radiated from radiators, which are aluminum radiators, which are accompanied by is active thermal control systems, which manipulates the temperature inside the for supply.
Ashish, the
The health
slides
of
are
the
visible,
space station.
but the sound is
Next
breaking.
slide, Rahil. Uh, sorry, sir, your voice just cracked. Okay, sir. The next part is about the propulsion systems. Uh, propulsion system part. So in the propulsion system, we are planning to use the system we are planning the gases that rocket solutions, methane propulsions for which we are going to produce methane in our own space station, and uh, low thrusters use the resistor jets. Next slide. Rahel, next slide. Uh, okay, the third part was about the low thrust needs thrusters, which are the resistor jet, which we'll be using for dodging the debris on smaller scale for debris of bigger dimensions. We will be using actual rockets, methyl propellants. Uh,
Can somebody else try presenting this part? We are
more
not at all
force
able to
change
follow
in
you
force.
because your voice is breaking and we are only hearing bits and pieces. So we are not able to make out what you are
This
trying
was
to say.
about
Maybe Rahil or somebody try present this part.
Yes, sir, I can
our
present. Sir, am I audible, sir?
Yeah, you are loud and clear. Maybe you can just speed up.
Okay, sir. So from here, propellant resistor jets. So as we talked about different propellants which we are using are for different needs. So this is basically for our low thrust needs. and this will be utilizing the waste gases which will be collecting from the um, ECLS systems or other laboratories, and this will basically provide thrust by heating. And over here, which we see as the name suggests, is the resistor jets. So it basically works upon a resistor element. There's a resistor element or an incandescent filament which heats up the gas. Because of that, it will expand the gas, and which will be in turn expelled by the conventional nozzle. And hence, this is also called as the evolution of the traditional cold gas thrusters. And which we know cold gas thrusters are used everywhere, which are the simplest form of rocket engine available. And hence, this is a brief about resistor jets. But we also have a disadvantage of this design that supply, but because of a design of a space station, we are planning it to be abundant. Next, we talk about in-station environment and electronic systems, because electronics are one of the most important systems in a space station. First, here we'll be talk about ECLSS. As I talked before, it is a regenerative life support system, and this thing basically consists of two key components. One is the water recovery system, and another is the oxygen generation system. As you can see the system over here in these two pictures, um, to be going ahead of. Now, this water recovery system consists about the urine processor assembly and the water processor assembly, and the oxygen generation system consists of the oxygen generation module and the power supply module. So the main operation of this is it will produce oxygen for breathing, replaces oxygen, all the basic life needs which we need on board, and also the all airlock depressurization and venting of carbon dioxide, etc. Here we can see a simple method of water recovery system. This is basically a system how you can convert your urine back to water, which can be further used for different activities or even drinking purposes. And this has been used for many years across the ISS. This is the system we'll be using. And this is the oxygen. So, so one of the most important things is the space tourism. Space tourism, as I talked about, is a glass dome. We'll be talking about the Great Dome, and hence the stargazing enthusiasts can enjoy seeing heavenly bodies through the telescope like Celestron. And we'll talk about 3D printed spacesuits, which we'll be using for spacewalk outside. And in different research and experiments, we have 3D printing facilities within one laboratory. So we know the restock missions are very time consuming, and hence we focus on three kinds of 3D printing: plastic, metallic, and food. Our main focus on 3D plastic is to print a spacesuits, which will act as a backup suit, and also it will act as suits for the spacewalk for the tourists in the future. Second is the metal 3D printing, making parts, spare parts, etc., or even developing rocket thrusters is a very essential component in metal 3D printing. And also, our main idea is utilizing the components of the space debris which we will be collecting in order to melt and reuse these metals for 3D printing. And hence, one of the another important thing is food 3D printing. Yes, it has been used already before, and this is one of the most important things for using in terms of low supply or also for tourists. Here we have space biology.
Am I audible, sir?
Yes, you are. You are audible. Please go ahead.
Yeah, yes, sir. Like we know that like food is one of the most essential need for human being to survive. So in space station, food is get delivered in
You may
subsequent
speed up your
manners.
presentation. Time is running out. You may speed up your
Yeah.
presentation,
So
please.
food is already present there in space station. So we can use medic rehydration station to distribute hot and cold water and dehydrated food to make it rehydrate. And Avighna is planning to cultivate vegetable and plants in space station in cultivation chamber. And for that we need fertilizers. And since for the fertilizers, we are using leftover food and human waste to create it in space itself instead of sending from the earth to the space. And in absence of gravity, plant will use light emitting diode to produce the spectrum of light for the plant growth. Next slide. Yeah, there are following method to preserve the food. So that are the free dehydration, irradiation, thermal stabilization, and freezing, moisture adjustment, and fermentation. But the most preferable method by Avighna is thermostabilization, because we were using heat pipe thermal cycle as an insulation to cool the systems, so that we can use heat from that system, and it will also help to lower the temperature of casing and also all the system inside that casing. And also, since we are cultivating food in the space, so we can use the method of fermentation to preserve that food, because fermentation is like it's a way to preserve food with nutrition. So there will be phase fermentation chamber which have like all temperature controls and environmental data will be maintained there. And space fermentation chambers will be tested on upcoming parabolic activities. And actually this is testing now, like it is not the firm methods. And also we can cultivate fruits and vegetables. Next slide. Biogas. Biogas production. This is one of the most important project. Like we can held in the space, because we are sending human disposal back to the earth. But instead of sending that disposal back to the earth, we are planning to attach suction pump to the toilet seats, which will push waste into the wasted chamber. And in wasted chamber, we will inject in wastage chamber we will inject methanogenesis virus, and which will convert that wastage into the biogas and the biological slug. And that biogas will nothing but the methane, and we will carry that methane by using pipe from the wastage chamber to the gas storage tank. And that methane we can use it as a fuel. And by using like by flowing that fuel through the flow pipes at high pressurized pressure, by rotating the turbine we can produce electricity by it. And biological slug we can use for the fertilizer in the food cultivation. Then there are following benefits for this biogas production, and that benefits are: we can produce methane in space. We can produce methane in space, which is very important or useful fuel for sending all.
Last 2 minutes.
Okay, sir. So one of the most important thing which we are doing is the space debris, which is also a topic. So hence we have two ideas. One idea is using this is for the micro debris or micro debris. So it is a helical structure with different the samples exploration with satellite idea, which will be of one of the limit size. Will see first. That's capture on basically going to using the lens. The main idea is that once your global population is over, it's over, we'll get the speed which, and after that we'll even from the space and hence it that
Rahul, you are not audible. Can you move the slide
we
and
get
go to the next slide?
We won't let it from the pivot as well. Now, it's that it will yes, actually in the scale.
Can you
The
move to the next slide, Rahul?
In the next slide, it's the space and hence now, yes, actually, let's in this slide, and the network from this. Can you view this slide? Millimeter separate. He said, I give you back to the next slide. The janitor factor.
Rahul, your slide is not moving.
Can you view
Your
this?
voice is also not clear.
Actually,
Voice also breaking. Can one of your team members
we
continue
are
with that?
viewing this. So which slide can you see right now? Is it the future?
The slide isn't moving actually.
Or let's I'll just share the content once again. Maybe the network. Sorry.
How many slides left?
Which slide? Is the field last slide which we should have shown? Now, the field, maybe can you see this?
Rahul, can you hear us?
Video which
Anybody from the team can
hear
hear
you.
us?
Can hear you. Can hear you. Yes.
Rahil, Anjali, or Ashish?
Can you please try, because whoever is, maybe can answer our questions.
Who is having connection, no connection issues can continue with that. I think Rahul's connection is having some issue. That's what we believe. Your voice is breaking, and slides are also not moving forward. In that case, Ashish was having some problem. Then Anjali can continue, I think, and conclude.
Yes, sir. So is the slide visible?
Yeah, slide is visible right now.
Okay, Anjali, continue.
How many slides left for your team?
This is the last slide. Last slide.
The last slide.
Yes, sir.
Yeah, please go ahead and complete this presentation.
Yes.
We are not hearing by anybody. We are not hearing from anybody.
Sir, am I audible right now? I can finish this.
Yeah. Right now
Am
we
I
are
audible?
audible.
Right? Okay, sir. So, concluding this is our second plan for the data collection, which using the janitor satellites. It is basically a small satellite will be released from our space station, which will go and capture the current satellites which have either been turned out or there are other management issues. So for this, we would need a global cooperation. So as soon as their satellite turns off, or they are out of fuel or in orbit of state at velocities, and hence approaching those velocities, and will basically go and the surface where it can be refueled, or we can do the maintenance, and if and after maintenance and refueling we can put it back to the orbit so that it can be used for the future, and also there won't be any remains of debris for the future, and hence we can conclude